Okay, what we want to do is we want to consider the area beneath the curve f of x equals x squared from 0 to 2. I do. Okay, so if we go from 0 to 2, and people who are, so like Greta, Katie, anybody else, Ina, anybody who's here on Friday, if you already get it and you want to try the second problem, go ahead. Otherwise, watch again and just see what happens. But the idea is, if we consider this area beneath the curve of x squared from 0 to 2, this is not the curve that I'm referring to. We're going to get to that in a second. But what we want to do is we just want to get our minds around what's been happening. We want to do that by doing the right-hand sum using 4 rectangles. So I've drawn this picture right over here of x squared, and I've divided up into 4 pieces. And we said that in order to evaluate the sum, we need to take the width times the sum of the heights. Okay? Now, what is the width of each one of these? 0.5, 1/2. Okay? Now, for this first one, the right-hand sum. So as I look at this first region right here, if I want to look at the right-hand side of it, am I going to evaluate it at 0 or 1/2? I evaluate it at 1/2. So that's my height. Okay? Whatever 1/2 plugged in there is. Then I will evaluate it at 1. Then I will evaluate it at 3/2. And then I will evaluate it at 2. And what I need to do is I need to figure out those heights. So, what is the height of the last rectangle? 4. What's the height of this rectangle? 3/2 squared is 2.25. 1 squared is 1. And 0.5 squared is 0.25. So there you have those 4 heights. So we'll add those up. We've got 0.25 plus 1 plus 2.25 plus 4. So 1 plus 4 is 5, plus 2.25 is 7.25, plus 0.25 is 7.5. Okay, we come up with a total of 3.75. You tell me, is that an overestimation or an underestimation? Overestimation, and you could tell because as you look at each one of these rectangles, I'm overlapping in each scenario, okay? You know that that's the case. So, okay. Boys. So, now it says the width of n rectangles. Ooh, boy. How did you figure out the width of 4 rectangles? What did you do? You took the first number of the interval, which was 2, minus the, the last number of the interval, 2, minus the first number of the interval, 0, and you divide it by the number of rectangles, 4. And so that's how we figured that out. What we did is we said the width was equal to 2 minus 0 divided by 4. So let's change this. And let's find the width of n rectangles. What would the width of n rectangles be? 2 over n. Okay, now I got to pause the video because I got to move around here. This is important. Okay, we took a break, but now we're back. And so for what x values do we evaluate the sum? Well, we take the beginning, whatever the beginning spot is for our interval, and we'll add on to that the width times I. Okay, what's the beginning spot of our interval? 0. What did we decide is going to be the new width? 2 over n, and we multiply that by I. So we get 2I over n. So again, we don't plug in 1, 2, 3, and 4. We plug in 2I over n for whatever value I is. And that's what we plug into the function. And now the magic will happen. Express the area as a definite integral and as a limit of a Riemann sum. So all this is what you have to write down. We are defining the area bounded from 0 to 2 of x squared dx. That is the current problem we are working through. That is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I. What is f of x? X squared. What are we plugging in for x sub I? So we got to take 2I over n and plug it into the function. Now, hold on, we got to pause. If you don't understand it, you have to ask right now. Because 1 represents our first rectangle. In order to generate this spot, this 1/2, what we do is that beginning spot plus the width times I. So that generates the 1/2. So Kelly, we're going to start with I equals 1 for our first rectangle. But when you actually plug in 1, you get 2 times 1 divided by the number of rectangles. And that's going to give you this spot that you actually evaluated. Yes, no? Okay. So this 2I over n gives us this 1/2 right here. What do we actually plug in? Well, we plug in I equals 1. That's to indicate the first rectangle. But the number that actually goes in the function would be 1/2. Okay? For that example. For here now we're doing an infinite number. Okay? All right, any other questions about that piece? Okay, times delta x. What's delta x? Which is 2 over n. Riemann. Riemann was a great mathematician. Okay, so now we're going to say that's equal to the limit as n goes to infinity of the sum from I equals 1 to n of, and I'm going to square this out. What's 2I squared? 4I squared. No, she's looking at her notes, and then times 2 would be 8I squared. Yep, you're right. 8I squared over n to the third. Now, here's what we're going to do, okay? John and Zach, please be quiet because I'm trying to teach. Thank you. We are not summing up the n's, are we? We're summing up the i's, okay? Because we're starting with I equals 1. I'm going to bring those n's and everything else out in front. So the directions say factor, leaving only an expression with I. So what I get is the limit as n goes to infinity of 8 over n to the third times the sum from I equals 1 to n of I squared. See how I brought that out and all I left in there was the I squared? Because you have n squared here times that n to the third. Good question. Any others? Okay, now here's the really cool part. Are you ready? Kelly, you have a question? So this 8i squared right here. So at the beginning, 2i squared was 4i squared. Times 2 is 8i squared. I pulled the 8 out. I left the I squared in there. I can factor it out as long as it's not an I. Because we're adding up the I's. I got to add them up first before I get rid of them. Yeah, I'll show you. I'll show you. Look at what we're doing, okay? This is a really interesting piece here. We are taking 1 and plugging it in. We get 1. Then we're plugging in 2, we get 4. Then we're plugging in 3, we get 9. We're adding up the first squares. Now, this is really cool. I got to pause the video. Okay, so we did our mathematical induction earlier in the year, and now it's time to plug it in. So what I have is the limit as n goes to infinity of 8 over n to the third times so I replace this. I put in an n times a 2n plus 1 times an n plus 1 divided by 6. I put that in for my summation piece. It's on the board. We used mathematical induction for the beginning of the year. Now, you guys, if you want to see how I actually get those, we could do that after class one day, and we could do mathematical induction all over. But we did those, and you guys came up with those exact formulas for mathematical induction. We know that those are true. Yep, we're just putting them in. Now, look at what you have left. We have an infinite limit. Do you know how to... did we not just have a test, boys? Did we not just have a test on limits as n goes to infinity? We did. You know how to evaluate this. And once we evaluate that limit, we have our sum. It's not 0. So, let's figure it out. Okay? The limit as n goes to infinity. And we have, let's FOIL that out. We're going to have a 8 times 2n to the third, right? And then we'll have a 3n squared. And then we'll have n all over. Well, I distributed that n through. So you had 2n squared plus 3n plus 1, and then we had this n outside. So I distributed that n through. Okay? So if I do that, now I'm going to multiply the 8 through. And I get the limit as n goes to infinity of 16n cubed plus 24n squared plus 8n all over 6n to the third. Now, what step do I do to evaluate this limit? What do I take out? Ben, you have a question. Yeah, you just have to make sure you show your work. Yeah, I don't want you to do this. 8 over 6 is 4/3, because that's, first of all, that's incorrect. You got this 2 left over as well. But yeah, I don't want you to just do that. I want you to, you don't necessarily, I mean, you don't have to distribute that through. I mean, you could do it, a little bit differently. That'll be fine, but yes. Well, I think so. If what you're asking is what I write down, then yes, you can do this. Okay, so what do I take out of the top? So I take out an n cubed, and I'm left with 16 plus 24 over n plus 8 over n squared. you need to write that. What? Okay, so now the n cubes, what happens to those? They go away. 24 over n becomes 0. 8 over n squared becomes 0. So you're left with 16 over 6, which is 8 over 3. You just added up an infinite number of rectangles. Shh, boys, girls. You just added up an infinite number of rectangles. You got 8/3. That represents the area, the exact area bounded between 0 and 2 and the function y equals x squared in the x-axis. And you just did it. Now, okay, you guys, Ella makes a really good point, and it was a point that was made on Friday. Some people said, actually, you did that. I did not. Robin Crawford, just 2 minutes later, decided to do x to the third and got the answer just like that. So, yes, Robin Crawford is a genius. If you guys want to... Tomorrow, we will go over example 2 and probably example 3. It'll go quicker because you see the process, but then you'll start to practice these. But you eventually want to be able to do this with, well, you know, we don't want to do like quintics, but we'll keep it nice and neat. The second one should be, what do I bound it from? 0 to 3. You should get 81/4. Now, I will show you a shortcut way of doing this next week.